I trained as a chemist, so I have a bachelor's and a PhD in organic chemistry, and I received both of those degrees in England, as you might be able to tell from my accent. I'm not actually from around here. And then I postdoced in the US at the University of Wisconsin-Madison, also in chemistry. Essentially, the state would like us to come up with a cost estimate for the economic cost associated with removing CO2 from flue gas. The basic question that they've posed to us is, what does it cost to remove a ton of CO2 from the flue gas emitted by, for example, a coal-fired power plant, using algae, given that algae can eat the CO2 and we can then turn that algal biomass into valuable products. So what's the overall cost going to be? The purpose of the research that's conducted in my group is really twofold. First of all, we aim to develop renewable fuel sources, so alternatives to petroleum-based fuels. And secondly, we aim to mitigate the impacts of fuel use. That's to say, we want to mitigate the pollution that's emitted as a consequence of burning and utilizing fuels. PBR stands for photobioreactor. Typically this is a closed vessel which is used in some kind of cultivation process. So in our research group we're using PBRs to cultivate algae. Essentially you can think of it just as a large cultivation system in which algae are exposed to light. They're additionally continuously circulated in order to ensure that all of the algae receive equal exposure to the light. Well, a great deal of effort worldwide is currently being directed towards the conversion of algae into biofuels. Algae contain lipids, that's to say oil, which can be processed into gasoline, diesel fuel, aviation fuel, in much the same way that crude petroleum can be processed. Additionally, algae contains protein and carbohydrates. Those carbohydrates could potentially be fermented to produce bioethanol, while the protein can be used for animal feed. Additionally, one can think about trying to extract certain high-value products from algae, such as beta-carotene, also omega unsaturated fatty acids, which are used for nutraceuticals, that's to say, as food additives. We have two other main biofuel-related projects at CER. The first of these concerns the utilization of lignin for the production of renewable chemicals and fuels. Lignin is one of three main biopolymers from which all biomass is composed. It's highly aromatic in character, and that gives rise to the idea that if you could actually break it down into its monomeric constituents, so the basic building blocks from which it's composed, then you would have a ready source of valuable aromatic compounds. And some of these compounds could additionally be processed into fuels. The other project on which we're currently working concerns the utilization of lipids, that's to say fats, animal fats and vegetable oils, for the production of liquid transportation fuels, and that involves a certain amount of catalytic processing, principally to remove the oxygen which is present in these fatty acid and triglyceride molecules from which all fats and oils are composed, all naturally occurring fats, I should say, and oils. The challenges are many. In fact, I hardly know where to begin. It's going to have to be inexpensive, and that's a problem because most commercial photobioreactors are anything but inexpensive. So you have to pay attention to maximizing utilization of the available light, given that algae growth is a photosynthetically driven process, so algae need light to grow. Temperature control is another issue, ensuring that the algae receive adequate amounts of nutrients. So the list is fairly long, and for that reason we've had to put a lot of effort in trying to design our optimal photobioreactor, if you will.